Thank you, everyone, for joining us on this final day. Today is more about working through what the potential is with Python, some of the things that you can do, and I'll also be showing some resources. To start off, this particular notebook, I'd like to credit to this particular website. They also have their YouTube video. So we'll discuss a little bit on what they do and how they do this. So it's more of a lot of times it's more of understanding other people's codes because most of the problems that we face today, at least at the learning stage, is problems that other people have already gone through. So they all have some form of data, some form of Python code or any programming language. So there's already resource out there. So a lot of times it's all about using those resources, finding those resources, and specifically understanding their resources. So this is one such resource. And in today's notebook, there's actually a couple of notebooks that I'll go through. But the first notebook involves building a dynamic CSTR simulation. So as a general reminder, I'm assuming most of you are final year students. And if you don't know this, that's okay. The basic understanding here is the general balance equation, where we write it as accumulation equals in minus out plus generation minus consumption. This generation minus consumption is usually a rate expression. So, what I mean by rate expression is it's a resultant of a chemical reaction taking place. So, for the simplicity of this particular notebook and this particular problem, we can just assume the rate of this chemical reaction is zero. As in other words, we can just assume that there's no chemical reaction happening. But you can imagine that that's not going to be the case most of the time when you're working in a chemical industry. So there's four main balance equations that we need to consider. That's the mass balance, material or species balance. You have momentum balance and energy balance. And in a lot of sense, momentum balance is something that you would also not consider directly in the equation because a lot of times you're looking at your reaction in a reactor at steady state conditions. So we're going to skip that as well. But we will include mass balance, energy balance, and species balance. So I've left the link to this particular website here on the notebook as well in case you want it. So mass balance is, and all of these equations, these balance equations are either time derivative or temperature derivative. So solving these equations will give you more information on mass, species, and energy balances, energy at particular instance of time. So, and that's usually a based on the residence time or the time it takes to for a reactant to pass through your reactor. And this example is only for one reactor. You can also have a sequence of reactors when you're building these models and carry out this particular analysis or simulation. So mass balance is basically you have mass going in minus mass going out. So this is the general form. For species balance, it's all in terms of moles. So you have moles of A going in, moles of A going out, A being the chemical component. And you can also have the generation minus consumption. But like I said, we're going to be considering this to be equal to zero, net zero, and that's the reaction rate. And you can write, obviously, you can write moles in terms of concentration and the reactor volume or the feed volume. Usually, this will be considered to be a reactor volume because that's where all the operations are happening, and that's the area of concern for everyone. And then we have the momentum balance as well. This is usually, you can also incorporate this in terms of the feed flow rate and the outlet flow rate. So that goes in pretty much there. And then we have the energy balance. For the energy balance, there's three main components: the internal energy, the kinetic energy, and the potential energy. These energies are individually assessed as enthalpy in and enthalpy in minus enthalpy out. This will be the internal energy. Kinetic energy in minus kinetic energy out is for kinetic energy, and then you have the same for potential energy. And you can also have terms like heat generated or work done on the system or by the system, which we will assume for this case to be zero because we don't want to complicate right away. But this will simply be another set of equations that you can have added to your simulation. Based on these differential equations, we basically get a series or a set of differential equations. And solving this set of differential equations is what is the first step that we are, or rather the main step that we are concerned with when it comes to simulation. So for a continuous stir tank reactor, we have the feed flow rate, the feed temperature, feed concentration. This will usually be the initial conditions. Then we have the reactor volume, and we have the output flow rate, the output temperature, and the concentration of the output. So these are usually the basic parameters that we deal with. Let's look at how we can do this using Python. So this is a code, like I said, is already written by the source. So I'm just reusing it here, and then we can, understand what this does. So you should be quite familiar with from yesterday's video on what NumPy and Matplotlib is. If you are not, then please do watch the video if you missed it. The third line is something called as SciPy. This is another package, and this particular module has this function called integrate, which we're going to, another module called integrate, and we're going to import a specific function from that, and that is called the odeint. So if you hover around the odeint, it will show the description here. So this is a function, and it's got a set of arguments. So it integrates a system of ODEs, ordinary differential equations, which is what we are dealing with. And it solves a system of ordinary differential equations using the LSODA method from the Fortran library. You don't have to worry about what this is. All we need to know is how we can use this function to solve our purpose. So it's used for initial value problems, which is what we are dealing with. And it can also work with stiff and non-stiff systems, which is a good thing. If you don't know what a stiff and non-stiff system is, a non-stiff system is you have a continuous time-dependent parameter that does not vary exponentially within a short span of time. But when it comes to a stiff problem, there's almost a discontinuity within the parameter depending on the temperature, depending on the time. So a lot of times, normal differential equation solvers will not be able to solve for stiff differential equations. So this function can do both. So that's always good to know. And you can read about it later on if you're more interested in that. So that's what this function does. So as you can see, some arguments are optional, but you can pass some arguments as a tuple. So we will be looking at that today. Obviously, we need to pass in the time points for which to solve for y. Why not will be the initial conditions that we pass in, and y is basically all the differential equations. So let's see how this works. First thing I'm going to do is import this, and the second cell that I have here is a function definition called vessel. Just as a quick reminder, you don't need to start off when you're writing your own code. Don't start off with a function. Usually start with everything that like all the operation that you want to do, like setting up your differential equations, the initial parameters, and things like that. And then if you think that this needs to be done or solved repeatedly, you can simply, instead of writing the entire code, you can put it in a function definition. So I think exercise 3 will help you, understand how to set up a function definition. So there are 4 main inputs for our equation. QF is the feed volumetric flow rate, Q is the outlet volumetric flow rate, and the units are given here. And CAF is the feed concentration, TF is the feed temperature, and small t is the time interval. So our particular problem concerns 3 states. That's the volume, concentration, and temperature. So what we are doing is we're storing these 3 states in a list called X. X is a list. And you can see that this vessel definition requires that argument. So we will pass in at the position 0 the volume, at position 1 the concentration, and at position 2 the temperature. This is actually index and not position. Then we set the reaction to be 0, the reaction rate to be 0. So if you have a reaction taking place, you can have the have an equation here as well for the rate of reaction and turn it into a differential equation with respect to time and concentration. Then there's the mass balance equation. Mass balance here is simply with QF minus Q, and this is with respect to this is a derivative of V, which is the volume with respect to time. And then you have species balance as well. This is written off from the chain rule. So if you want to read about how this is done, all you have to do is click on that link in the notebook. You will come back to this website and you can read about this. But I'm sure most final year students know at least where this comes from. So this is a change in concentration with respect to time variable. So this will be feed concentration feed flow rate times the feed concentration minus the output flow rate times the output concentration. And this is all with respect to volume. And you also have RA, which is the rate, which in our case will be 0. And then for the energy balance, you have a similar type of equation, which is basically in minus out. So then this function will return all the derivatives. So it will basically solve for each of these derivatives, and it will, actually, this function will only return the derivatives as it is. So it doesn't return the solution. We'll look at the solutions soon. Like solution, I mean how to solve these differential equations. So this is an initial value problem. So we need initial conditions for all the states. So we have the initial volume set at 1. I think this is volume should be 1 liters. So there we go. And then we have the concentration in the feed to be 0. Temperature T naught as 350, and I think 350 is in Kelvin. And then what we're doing is we're storing all of these initial values in a list called Y naught, and we just store it in this list. Sometimes it's easier to pass everything in a list, so that's the only reason why we're doing this. So let me first run this function definition cell and then run this cell. So if you want to take a look at what Y naught looks like, you can, I'll put a cell below. You can say Y naught, and this will show all our initial parameters. So this is how all the initial conditions are stored. Then you can have the time interval in minutes. Time interval, we're using this function called linspace, which we saw yesterday. So it's going to generate about 100 points between 0 and 10, and time's always starting from 0. The time array will look something like this, starting from 0 all the way to 10, and you have about 100 points in between. Then we have the inlet volumetric flow rate. Now here I've used numpy.ones to randomly generate some randomly generate some inlet volumetric flow rate. If you have your data, you can directly have your data input here. Sometimes if you're using some type of a electronic device to record your flow rate and things like that, and it generates a file that has information tabulated on the volumetric flow rate, you can use a package called pandas in Python. So this is another package. Pandas is a data analysis library. You can use this package to load CSV files or Excel files onto Python. So I didn't have time to go through this documentation because this is quite extensive, but it's also very simple. Kind of similar to NumPy, but it's I feel like it has more functionality and it's much more simple. So you can use something like pandas. So maybe I'll write a comment here. If you have a CSV file, or it not just CSV file, it takes in any file. Pandas has that capability. So if you have a CSV file or any other type of file, you can use pandas. So if you're interested in this, I will leave a link to this as well. So I'll just leave this link here. In the meantime, if you have any questions so far, please feel free to ask. So you can use pandas to load your data, but what I'm doing is I'm just making an array of ones, and the length p. Remember, for the function ones, we need to pass in the size. So if you do this, okay. So you have to pass in the size or the shape. So what I'm doing is I'm passing the length of t. So this is the length of the time array. So you need a data point for every point of time. So if you're recording your data on this particular reactor, you're basically at every periodic instance in time, you are getting your input flow rate and input concentration and so on and so forth. So that's why you need to have the same length for QF. And here, just to make sure that it's not one, I just multiplied by 4. So then at some point in time, I'm changing the concentration, or sorry, I'm changing the feed volumetric flow rate to 5.1. So this array will look something like this. It's 4 up to about the 50th time instance, and then after that, it's all 5.1. That's the volumetric flow rate. The output volumetric flow rate, we're keeping it constant. I know that this is not usually the case. You can always have varying volumetric flow rate depending on your feed flow rate. So that's something, if you have your data on, you can always include here. Then there's the feed concentration. I use the same process. I have an array of ones, and I just, actually, I don't know why I multiply by 1. We can change this to maybe 2. And then after about the 30th instance, we are changing the feed concentration. So let me run the cells before as well. So we have the feed concentration. Then there's the feed temperature. We start with 300, and then we go for 325 after some time instance. So the feed temperature will look something like this. Normally, this is random data that I'm generating. Normally, you will have some data of your own. So if you use pandas library, you can process your files quickly. Then we're storing the results. So for every time instant, we do have volume, concentration, and temperature that is generated or that is recorded, and we need to store this result somewhere. So what we will do is we'll simply store them in simple variables like this, V, C, A, and capital T. And we need this in this format for our ODE solver. So this is where we solve these differential equations. So as you can see, it's a simple for loop. It's not very complicated. It's very simple, but let's see how this works. We need this simulation to happen for a range of our time instance. So basically, time going from 0, I think we chose 10 minutes. So 0 to 10 is what we need. So to simulate, we have this inputs, which is a tuple. So in this inputs tuple, we are accessing Q, QF, CAF, and TF. And this I will get each individual value from an array like this for each instance in time. Then we have a time step here. TS is for time step. We are going from time I to time I plus 1. So it's like going from 0 to 0 to 1. So, or 0 to the next time instant. So that's what the time step is. And then Y is a set, Y is where we store our results. Results as in results from the ODE solver. So this ODE int is the function that we imported earlier on in the notebook. So this requires some arguments. In the first argument, we're going to pass in our function itself. Remember, this is also called calling our function. This is where we are calling our function vessel that we defined before. So if you want to go back all the way to see what this function does, so it stores all of the equations and everything, and it returns all our differential equations. So instead of having us typing each of the equations and putting them here in this function, we just pass in our function definition. So it's as simple as that. Then we have why not. I think if I'm not wrong, why not is a list of initial parameters that we had, which is the initial volume, initial feed concentration, and I think initial volumetric flow rate. So we have that, and TS is the time step that we are passing in, and args is one of the arguments with ODE in. So if you look at the function, this function has a parameter called args, where you can pass in more arguments. So extra arguments to pass to the function. That's what this does. And we have to pass it as a tuple. So that's where we are passing in this inputs tuple that has the time instance of feed flow rate, output flow rate, feed concentration, and feed temperature. So all of these are passed in. So this ODE int function will solve all of the set of equations that we have passed, and essentially for all the other parameters that we have. And then it will store the result in Y. So Y will be kind of like a list.
Ethan,
Yes,
that arcs is equals to or it is hyphen? I'm
it's
not.
equal. It's equal to. Let me forgot to enlarge the.
Now it is visible. Thank you.
Okay.
So when we are calling a function, we can write like this equal sign there.
So yeah, so this is a ODE int is a function that we just
Function, yeah.
imported. So it takes in arguments. So you can pass in arguments, extra arguments through one of the parameter
Okay.
called args. And essentially you don't need this args. Sometimes some functions you don't require this. If so, usually some functions you need to pass in the arguments in the same order. So that's when you don't need to use the args equals whatever it is. So in some instances the position of the arguments do not matter. So in that case what you do is you can just say inputs instead of args. Or sorry, in that case, you need the args equals inputs. That way it knows which parameter inputs is. Okay, so next, what we do is we need to store the results of the volume, concentration, and temperature. So what we do is we access these specific results. So I'll show you what how this storage happens. And then what we need to do is adjust initial conditions for the next loop. So to adjust that, we need to go for we need to use our Y naught. So we need to reset Y naught as the last condition that we had. So let's see what y of -1 does. Remember, in indexing, when you call -1, it gets the last element in the array. So here, y naught is basically this array that has volume, concentration, and temperature. ODE int will solve between the two time steps using all the initial parameters, including our differential equations, and it will store the volume, concentration, and temperature. These volume, concentration, and temperatures are basically what we have in our differential equations. So if you go up, it's dV, dCA, and dt. So this is what we are getting. That will be the solution: volume, concentration, and temperature. So this solution is stored in a list called y, or in an array called y, and we only want the final entry in this array, which is for a time of t of I+1. So this will be stored. The first element 0 is the volume, so volume will be stored there. Second element is the concentration, so that will be stored there. And then y -1 of 2 is the third element, which is the temperature, and that temperature will be stored here. So these results for the next iteration, will be put back into our function here. So this will go back in y naught. Remember, y naught was also a list of volume, concentration, and temperature. So I hope this was clear. I know that this indexing can be a little confusing, but all it's doing is it's simulating between two time steps, and takes the final entry to the next iteration. So that's all that this loop is doing. Let me know in the poll if you're able to follow this. And if you have any questions, I'll be happy to answer them. Okay, so it looks like most of you are able to follow this. So what we'll do now is we need to construct this results and store all the files, all the data points in a file. So we can say data equals numpy vstack. We can use our vstack function to stack up all of the parameters that we want in our file. So this will stack everything vertically. And then this data is stored, or we're actually also taking a transpose here. If I do this, here and run this file. So our data will be stored something like this. So we also use the numpy save text function. You can use the numpy save text, or if you're using pandas, you can also use a function in pandas. But since we know numpy, there is a function called save text. So this will save a file here as data.txt, and this is all comma separated data. So if we open this, let's say you want to make a file and then use this file to plot something later on, you can store it as a file. Okay, let's see if it downloads. Okay, downloaded the file. And then we can open the file later on. So this file will look something like this. It's a pretty large file with just numbers. So you can add headers to this if you want. But that's just adding more arguments to the code. So for now, I thought we'll just keep it simple. But you can think of this as a data file that has the time instance first in the first column. Then you have the feed flow rate and output flow rate, temperature, feed concentration, volume, output concentration, and temperature, output temperature. So that's what this file will have. And then here we're making a bunch of plots. So here's a new function that you can think of, and that's called subplot. So the moment you use this function, Python will know that, okay, you're making multiple plots in a single figure. So the first line we say plt.figure. So then we say plt.subplot. So this is a function that adds an axis to the current figure and or retrieve an existing axis. So subplots is basically like having multiple plots in one figure. So the way this numbering works is we say the size to be 3 comma 2, which is kind of like a matrix with 3 rows and 2 columns. And then in that 3 rows and 2 columns, the very first figure will have all of this. And then the third figure will have all of this. Fifth figure will have all of this. There's no particular order. You can change this if you want. I just thought this to be more convenient when we actually see the figure. So the second figure will be something like this. 4 will be something like this. So if you have 3 rows and 2 columns, you will have 6 figures. So we have 6 subplots here. So the first plot is basically we're making 2 plots here. So there's plt.plot twice. So one we're doing time versus feed volumetric flow rate, and then time versus the output volumetric flow rate. And line width is an option within the plot function that will set the width of the line. So you can change this if you want. You can I will reduce this. And y label is a function that sets the y-axis. And legend basically gives the legend in the form of a list if you include it, inlet comma outlet. And it chooses the best location by default. So if you want to change this location, you can say top, bottom, or whatever. But default is usually good. So then the third figure has time versus the feed concentration. Again, I have a line width here, and the rest are pretty much similar to the first section here. So this is done for temperature and time versus temperature, time versus volume, time versus concentration, and then you also have it for time versus output temperature, or the I forget what it's called, but you know when you have the contents in the reactor coming out. You measure the temperature when it's out of the reactor. And then finally, we do plt.show to show all of this together. And we also, if you want to save this, you can also say plt.savefig, and you can give it a name. You can say combo.png. You can give an extension, and you can give the dots per inches, dpi, equals, say, 500. And then you can run this. So this will display the figure. Okay, there was a problem here. So it says raise value error. So top is not valid. So that's good to know. So best is the default option. Here's the other options that you can give. I guess I can just leave this to be best. And when we run this cell, this is our plot. So this is how it looks. We have the flow rate versus, all of this is versus time. So we have flow rate versus time, concentration versus time, and temperature versus time. And if you scroll up here, I think our file should be stored, or our figure should be saved, combo.png. It will look like this. You can obviously download this and store it somewhere and use it in your manuscript or any report that you write, or even in presentations. So with that, this notebook is done. We have another notebook, but do you have any questions up to this point? Okay, no questions. Here's the second notebook, but first I'd like to share this resource with you. There is a package called Cantera, which if I can find it. So there, as you can see, I've opened so many tabs here. These are all GitHub pages where people have their code. So this person has a reaction modeling using least squares problem, and he basically models the Michaelis-Menten model for a enzymatic reaction. So you can take a look at their notebook. And GitHub is where usually people upload their code. So if you have an account there, you can access other people's code and use it as your own as well, depending on how their code is licensed. So this is Cantera, which is another source that I found. They have a lot of examples for their software. So if you go to Python examples, they have so many different examples that you can look at. And I've picked a few that I've put up here on this notebook. So I will leave the link to this resource as well in the notebook. So I'll leave a text and paste this source. You do need to install their package. So Google Colab does not have, like I said in our previous few videos, that it doesn't have all the packages installed. So we're going to install their package. And the way to install is we call this pip command. So first on Google Colab or any other notebook, you always start with the exclamation point or exclamation mark. This is indicating that this is a bash script. So you can read about what they are if you're interested, but just remember that this is not a Python code, or this line is not in Python. This is some other language called bash. So we install packages using pip install Cantera. So usually all of these documentation have information on their website on how to download their download or install their package. If I go here, install, it says Cantera can be installed using pip. So if you do this, they give information on how you can do so. So if you're using Python directly, like in PyCharm or something, and if you're using a Python interpreter, then you can just say pip without the exclamation mark. So this is how you download a package. So here we're going to download this, and each time the notebook disconnects, remember you have to re-download or reinstall the package again. So that's one drawback of Google Colab, but I guess it's also to help you out. If it's on an IDE, you only install the package once. You don't need to always install it. Okay, while that's running, let's just quickly go through the code. I'm not going to explain every line in the code. We're just going to see the capabilities of this package. So this particular example is for solving a plug flow reactor problem. So this involves a surface chemistry. Specifically, this problem is for the partial oxidation of methane over a platinum catalyst in a packed bed reactor. So when we just quickly run this cell, so it gives distance versus the concentration of methane, hydrogen, and carbon monoxide. So this is really good information for us. And it also says results have been saved to this particular CSV file. So you can open the CSV file. CSV files are usually like your Excel files. So you can open this in Excel. CSV stands for comma separated files. So that's what it is. And then there's another example for a CSTR with steady state inputs and periodic interior state. So this is for oxidation, or rather, this is for a formation of H2O. Finally, this 2 should be here. So this is their code. The way you work with this package is you import Cantera, and then you just use any other package that you want to run this code. So let's just quickly look at what this does. So this is a continuous stir tank reactor, but there's some sort of periodic behavior happening here. So it looks like at certain time instance, they flush the entire reactor and start fresh. So the legend says that these lines are basically concentrations of different components. So this is mass fraction, and then mass fraction versus time. So this is a nice plot for describing such a reactor. Then there's also an example for mixing two streams. And let's just run this. So I don't want you to go through the entire code trying to figure out what it is, but I think it's important to just see the capabilities first, and then if you're more interested in it, you can always do this on your own time. So this takes in temperature, pressure, density, and mean molecular weight and phase of the matter as gas. So then it gives you information about the different fractions, the mass fraction, molecular fraction of each of the components. And I think AR is basically argon. So this is what this particular example and code does. If you want to reuse this, you can always reuse it, and just change your input parameters the way you want. If there's a function that you want to change, you can always do that. Then there's an example for the cell voltage of a lithium ion battery. So if I'm not wrong, this measured the cell voltage with respect to, or rather, cell voltage with respect to state of charge. So at 100% charge, you have the highest cell voltage. So these are some experiments that you can run, that you can simulate using Python. So that was the last example that I had. For more examples, check out their website. They have plenty of examples. They also have a tutorials page where you can go through all of the code that they've written. Okay, so with that, I guess we can conclude for today, and I will just stay back for more questions. And if you like to watch more videos, please do consider going to the channel, the page. There's all the videos from today's lecture that is posted. And please do subscribe if you like. And I will be coming up with more videos in the next few months, and hopefully for a long time. So if you want to learn from me and continue learning in this field, do consider subscribing.